Okay. Questions?
In chapter 4, the second topic, the effects of electron donating and withdrawing crystal masses, I don't get it.
You don't get it. What don't you get?
What you mean? Like, what are we supposed to
be? Okay. It's been a while, but what we did was we looked at, for instance, this would be called benzoic acid, so its equilibrium, it would be in equilibrium with its conjugate base, and H+. And so what kind of group, let's say I was to add a group to the benzene ring, what group would cause that acid to become stronger? Okay, so my question is, this is a group, and so I could put an NO2 group on the ring, I could put a CH3 group on the ring, I suppose I could put, well, let's just see between those two. Which group would cause the acid to be stronger? The nitro or the methyl? Any thoughts? David?
It would distribute the charge better since it would withdraw some electrons.
Okay. So I hear a nitro group. Right. So if you had this problem on the exam, you could skip it and then try and come back to it at the end if you had time. But my suggestion is, if you weren't quite sure, let's go back to foundations. What do I have to do to that acid to make it a stronger acid?
You're going to want to figure out if there's different ways that resonance will work to spread out the charge.
Okay, but I want it basically boiled down to 3 words.
Stabilize the conjugate base.
Stabilize the conjugate base. That's 4 words, but that'll work. So stabilize the base. So if I want to make this a stronger acid, I need to make this more stable. How am I going to do that? Now, the question of spreading out the charge. So when you have something that has a negative charge, what do you want to do? You want to spread the charge out. You want to pull that charge away from the carboxylic acid, or from the carboxylate, which is the deprotonated carboxylic acid. So then the question is, which one of these 2 groups is going to pull that electron density towards it? Is it going to be a nitro group or is it going to be a methyl group? Well, we have to remember, so what is the nitro? The nitro has a double bonded to the O, and it has a plus charge, whereas the CH3, remember that all alkyl groups, the carbons are slightly positive and the carbon's slightly negative. So what's the carbon going to do in CH3? Is it going to pull the electron density, or is it going to push electron density into the ring. It's going to push the electron density. Is that what we want to do in this case? No. We want to pull it. So what's going to pull it? A nitro group. Why? It can be as simple as there's a plus charge there. So that plus charge is going to take electron density from the ring. The ring's going to take electron density from the C double bond OO minus group. Now, if this was a basic problem, meaning that we started with an NH2 and we added water to it and we formed an NH3 plus then our hydroxide, and I said which group is going to form a stronger base, and I gave you that nitro group and the methyl group. Which one would it be? It would be the methyl group, because same basic principle. In order to push this equilibrium to the right, and it is an equilibrium, in order to push it to the right, what do I need to do? I need to make the product more stable. I need to make the ammonium ion more stable. How do I do that? In this case, since it's positively charged, I need to push the electron density into the ring. So, depending on the molecule that I'm looking at, the answer could be one or the other. It depends on what the product is. So that's what I meant by those. That's the kind of problems. And we had done some of those in the top hat questions that I had sent out to you. So that's what that meant. What else?
When we're working with SN1 and SN2 substitution, how does the conformational change between the initial and the final product? I can't figure out how it changes quite with the shaping.
So for SN1 or SN2?
Is SN2 where it flips?
Yes.
Yeah.
Okay, so for SN2, they asked this morning, and the only reason I say that is because when I put the videos up, what I told them this morning was, I don't know what questions you're going to ask. You may ask different questions than they asked this morning. If you wanted to take a look at their video and see what questions they asked, just like they could see what questions you asked, then there might be a full set of questions answered there. So one of the things that the question was, well, how do you write a mechanism for an SN2 reaction if the molecule's chiral? And so an example of that would be, let's say I write my chloro, I'm going to write this as, this is R2-chlorobutane. And I know it's R because I put the hydrogen in the back to make it look that way. So then going from 1 to 2 to 3 is clockwise. So if I gave you this reaction and said, write the mechanism of the, let's say, reacting hydroxide with R2-chlorobutane. You're going to have to show the stereochemistry of the final product as well as the stereochemistry in the transition state. So I guess to make it more relevant and people's ears usually perk up, if you look at some of the older exams, mechanisms are usually like 15-point problems. But remember, exams don't match; they don't add up to 100 because I don't have the kind of time to figure that out. So I just have point values for each question. So whatever it adds up to, it adds up to. If it's over 200 points, then I know nobody's going to finish it. So then I either leave it the same or I cut down on the points. But it's always a percentage. And what I'm trying to say here is that the first step in this mechanism is to take this arrow, have it attack that carbon, and have the chlorine leave. So literally those two arrows are 1/3 of the problem. So you want to make sure that you put those in there. Okay, because that's the first step.
Would we draw that arrows should always be attacking components?
Absolutely. Because remember, arrows show movement of electrons. So this carbon is slightly positive, so that minus has to move towards the positive. And then when breaking the carbon-chlorine bond, the electrons are going to the chlorine. So they have to go in that direction. So the transition state then would look like this. Your OH attacking the carbon, and then as far as the bold, in-plane bold, and dashed wedges, they're set by the molecule. So the methyl group is in the plane, the hydrogen is on the dashed wedge, and the ethyl group is on the bold wedge. So you for a non-chiral molecule, or if I show you a chiral or a non-chiral molecule, you can put those three groups anywhere you want, but if it's chiral, you've got to make sure they match up. So there's my transition state. Another third of the problem. And then when the chloride leaves, the OH ends up in the plane attached to the carbon. The CH3 is in the plane. The hydrogen is dashed. And the ethyl group is bold. Plus Cl minus. So the final stereochemistry of the product is going to be opposite in configuration of the original. And so you can see that when the OH attacks, the bonds flatten out, and then they get kicked off to the other side. And I will check the configuration of the final product to make sure that OH is 1, ethyl's 2, so that it's going in a clockwise, so that you did write that you wrote the inverted configuration.
So no matter what, if it's a chiral carbon, it will flip configuration?
In SN2. SN2 always has an inversion of configuration. That's always. But I have to show you the chiral. I have to show you the molecule initially chiral in order for you to know how to react it.
Don't flip if the group, the halide that's knocked off is not the highest priority.
That's the exception to the rule that we're not going to get into. The predicate, the basis that the inversion of configuration will occur, R becoming S and vice versa, is always that the number one group is the leaving group, and in the final product, the number one group is the nucleophile. And I'd have to work really hard at this point to find an example of what that you could understand at this point. where that wouldn't be the case.
And there's a version that it's an 8 chiral molecule versus a chiral one, right? Or
There's
is it
only
all
inversion.
versions?
There's only inversion if it's a chiral center. If it's an achiral center, it still goes through the same mechanism. But since there wasn't an R and S configuration to begin with, there's not an R and S configuration of the final product. So that's what I was saying in the transition state in the final product. You could put any of the 3 groups on any of the positions because there was no beginning stereochemistry. When there's a beginning stereochemistry, you've got to go through the entire inversion.
Just like on the exams, like on some of the past exams, you've written out the chemical structure. Would you care if I translated it to the chemical structure instead and just solved it that way? Or does it?
What do you mean by the chemical? What do you mean by chemical structure? I mean going between line bonds and going between something like that. Yeah, you can do that, except where I give you bold and dashed wedges.
Okay.
Then you have to use my bold and dashed wedges. But if I said, what's the product of this reaction, you could just simply write the product of that reaction as using the line bond structure. Yeah, you could do that. Or if you wanted to, you could put CH2s and CH3s in here and write the final product as CH2, CH3. I mean, I'm going back and forth, and sometimes I'm even using CH3s and line bonds in the same structure. It's all the same. So yeah, as long as you're.
I was just making sure you did have a preference.
No, I can read it. I can translate most anything,
Okay.
if it's translatable. Right. Remember, don't make me guess because I always guess wrong.
So do we need to include transition states?
Yes. So in an SN1 or an SN2 mechanism, plan on writing the transition states for each step. And that includes the SN1.
What would the transition state look like using the line?
It could be part. It would be the Br minus coming into the carbon, and then the chlorine delta minus, and then you would still have it like this. Only now I've got 2 H's and a propyl group. So if you want to, you could write H, H, and then like that. Or you could just write it CH2, CH2, CH3.
At that point, it doesn't matter where you put the H's and where you put the...
Because this is not a chiral center. And more importantly, I didn't give it to you. So you're only locked into the transition state if it's a chiral center and I gave you the starting stereochemistry. I could do this. I could say, there's a methyl group. Now it's a chiral center. But since I didn't tell you by bold and dashed wedges which one you're starting with, you could put that methyl group anywhere. And I'll say in the problem, show the stereochemistry. I'll probably say show the stereochemistry where necessary, but I'll probably just say explicitly show the stereochemistry.
Can we talk about ranking of image projections?
Okay. So you got a particular one in mind? Let's say that I gave you 1, 2, 3, 4, 5, that this is 2-methyl pentane, and I said we're looking down the carbon 2, carbon 3 bond. So if I said draw the 3 staggered and 3 clipped structures of 2-methyl pentane, looking down the carbon 2, carbon 3 bond, you first of all have to translate the 2-methyl pentane onto the Newman projection. So we do that by saying what's attached to the front carbon, carbon 2. And I would look at that and I'd say, well, carbon 3, the carbon 3 is already built into the Newman projection. So it looks like 2 methyls and a hydrogen. So then what you would want to do is, what I do just to kind of make sure I get them all done at the same time, is I'll put in all those groups. I might even draw the eclipsed conformations and draw those groups into the eclipsed conformation. So I would have the front carbon always having the CH, 2 CH3s and an H. So my preference is to hold the front carbon the same. But if you want to do it different, you could have the back carbon the same.
Now, does it matter on what's on the front carbon?
No, it does not matter whether the methyl group is on the left or the right. Like if I put one methyl group up, doesn't matter where the other ones go. Now that we know about chiral centers, if I gave you a molecule that had 2 chiral centers in it, which I did for the take-home quiz, it turns out that there's 2 different diastereomers that you could be drawing the Newman projection for, which means there's 2 separate answers. And that's why there were 2 completely separate answers and answer keys for the take-home quiz when I asked you to do this. Because the molecule I had given you had 2 chiral centers, and so therefore if you drew one diastereomer, you got one set of conformations. If you drew the other diastereomer, you got another set of conformations. But in this case, there's no chiral centers, so that's not a problem. All right, so what's on carbon 3? Looks like 2 H's in an ethyl group. So does it matter where I put those? No. Because I'm going to now rotate the back carbon and form all the different conformations. So there's my back carbon, 2 H's and an ethyl. So now let's go ahead and rotate clockwise. So I'm going to rotate the ethyl group to the top left, and then the hydrogens go in the other 2 positions, and then I would continue and rotate the ethyl group to the top right. And so there are my 3 conformations. Again, if you want to hold the back carbon the same and rotate the front one, it doesn't matter to me. The one thing you do not want to do is to start rotating both carbons, because there's no guarantee you'll get all 3 different conformations. Okay. So then I could do the same thing down here, 2 H's and an ethyl group, and then rotate that around. And so there's my 6. Don't ever tell people what time it is. Okay, so let's do this by give you some chance for some participation points. And I'm going to have to make this a word answer. Okay, now let me... That's not helpful. Okay. So let me think. What's going to be my question? So of A through F, what's the most stable conformation? And if there's more than one because they're the same, then type out both letters. So what's the most stable conformation of those 6? A through F. And you might as well rank them because we're going to go down the line here. Is there anybody who hasn't answered? Not now. Okay. Okay, so I see a lot of A's. I'm going to interpret the one that has everything together as not following directions. Okay. Yeah, I know. I just asked for the first 2 to begin with. So, first 2 is, I see AB, 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 another AB, A and B, so that seems to be the most popular answer. Don't start switching on me. And that. So which one are the most stable? A and B. How do we tell? First thing we're going to do is look at Gauss interactions between non-hydrogen groups. So I see a Gauss interaction here, 1. I see a Gauss interaction here, 2. I see 2 Gauss interactions here. So that means that A and B both have 1. C has 2. A and B are going to be more stable than C because of the number of Gauss interactions. Now I want to go a step further and examine the Gauss interactions to maybe break the tie between A and B. So between A and B I see a methyl and an ethyl, and between B I see a methyl and an ethyl. Same interactions, and so A and B are the same, so they're number 1. They're the most stable. Okay, so it's number of interactions, then look at the specific interactions. The bigger the group, the more unstable the interaction. So you'd want 2 smalls versus a small and a large. And then C would be number 2. So now let's look at the last 3, D, E, and F. Let me just double check here and see. Okay. So tell me the most stable of D, E, and F. And just use a capital letter, or if it's 2, use 2 capital letters next to each other with no space, no comma, no and. Just 2 letters, 2 capital letters. So that way it aggregates them all together.
What are you asking for?
I'm looking for the most stable. The most stable of DEF.
Oh.
And if there's 2 capital letters side by side. Okay. Follow directions. So I see D all by itself as the major answer. Okay. So in the case of eclipsing, we want to look at eclipsing interactions. D has how many eclipsing interactions between non-hydrogen groups? 0. E has 1. F has 1. So that makes D the most stable. So this one's I guess in my numbering scheme, that's number 3. And then what about E and F? Same or not same? Energy. Same or not same energy? Same? So we got methyl-ethyl eclipsing, methyl-ethyl eclipsing. They would be number 4. They would have the same energy. So the critical step here to maximizing your points, right? Because we can always talk in terms that arouses everybody's interest in points. But, getting it correct is helpful too. You got to look at the carbon and you got to make sure you set this up correctly. So make sure the front carbon has the proper groups. Make sure the back carbon has the proper groups. And that is the question of just rotating around, looking at the number of Gauss interactions to set the stability, and then if you have ties in that between the number of Gauss interactions, what groups are Gauss? The bigger the groups, the more unstable the interaction. So that's how we would do a Newman projection. And what I set up, in this roadmap thing, which it's not even my term, it's a term from one of my former students that teaches at Ohio State, is in charge of all the organic at Ohio State. That would be a great job to have, to be the king of organic. Maybe. He teaches in a double-decker. If you've ever seen the video where he threw a paper ball up into the second tier, and they threw it at a basketball hoop and made it, and everybody got an A for that quiz, that's him. I don't do that. Right. No, this was one of those little desktop. This was one of those little tiny basketball hoops. But anyway, the roadmap idea here is that because the Canvas site needs a little bit of redesign to make sure that you can find everything. Little bit's probably an understatement, but this way, if you need more Newman projection problems, there are those and it tells you exactly what folder to go to. And then it has the answer, the narrated answer key. There are also some of these problems in the older exams. So the last 5 years of exams match up with our current pace, sort of. The previous to 5 years exams are all over the place because that was a much slower paced class. Okay. So that's, bless you, if you want to try those problems, that's where they're at. Same thing's true for cyclohexane chairs. Okay. So you're going to have to do a Newman, you're going to have to do a cyclohexane chair, you're going to have to do RNS, you're going to have to give me stereochemical relationships, you're probably going to have to write an SN1, SN2 mechanism, and then whatever else I decide.
Is there going to be something like on the last test, that last page, like those two last pages, like how it's kind of multiple questions on one topic? So I talked about that a little bit this morning. And again, the reason I say that's because if you're thinking about that, you can go back and watch what I did. Because you're like, I don't care what happened this morning. Well, you might, because it might be a question you didn't ask. Here's the question. Here's a question I could ask you, and I will ask you right now. And I won't do it by the phone, but so here are two reactions. Which reaction goes faster? A or B, or if they go at the same rate, C. Anybody need help on starting the problem? I need help. Help me. What should I consider first? What's the mechanism of the reaction? So is this SN1 or is it SN2? Hold up a finger or two, depending on which one you want. I see ones and I see all the right fingers. So it's an SN1 reaction. You never know. It's an SN1 reaction. Why?
Because water's too weak.
So water is a weak nucleophile, automatically makes it an SN1 reaction. You don't have to go to the chart, although if you did, you would find tertiary plus weak nucleophile SN1, secondary plus weak nucleophile SN1. So, and remember, I have to ask you the same mechanism. We can't mix mechanisms here. So these are both SN1. Okay? What's next? What do I have to consider now?
Well, like looking at tertiary and secondary carbons.
Okay, so I've got a tertiary halide and a secondary halide. So the question I should ask is what? In an SN1 reaction,
What's going to be the activation energy comparison of the two, and then you'll be able to use Huns.
okay, you went a little further you went a little farther in the explanation. What do I need to know? I need to know which one reacts fastest. Tertiary or secondary? In an SN1, which one reacts faster? Tertiary or secondary? Tertiary. Okay. Why? Now, why? This is where we get to the last page of the last exam. The why. Right? And then if you go back and you look at the last page of the last exam, the question ultimately was about forming a tertiary carbocation versus forming a primary carbocation. That was in the exam. In this case, we're really talking about which is formed faster, a tertiary carbocation or a secondary carbocation. What? Tertiary. Why? So now let's take it step by step. Tell me something about the tertiary versus, let's answer the question step by step. So where would you start first?
The alkyl groups and its effect on charge.
Okay. So the tertiary has more alkyl groups than the secondary, so which one's more stable? Tertiary. So tertiary is more stable because it's got an additional alkyl groups. Okay, so there's part one of the answer. My usual thing is like, so what? Give me the next step. But what is the importance about the tertiary carbocation being more stable? And our ultimate goal is, why does it react faster?
The more stable it is, the lower energy.
The more stable it is, the lower energy it is. I will accept that. Tertiary carbocation, secondary carbocation. And it usually says use a reaction coordinate diagram if needed. It's always needed. So whenever I use that phrase, something's needed. If needed, it's probably needed. So here's my reaction coordinate diagram showing that my tertiary is more stable than my secondary. What's next about in the answer, David?
And the lower energy.
It has a lower activation energy by whose postulate? Hammond's postulate. So Hammond's postulate says then that forming a tertiary carbocation, because it's more stable, has a lower activation energy. We're still not there.
According to Hammond's postulate, it would be closer to the most stable, which would be the prime. So the hill would be shorter.
Actually, the other way around. It would be closer to the reactants. Right. That would be a little bit more detailed, but that's fine. So now the final connection. Why does it react faster? Why is it formed faster? It has a lower activation energy. Who relates activation energy to rate? The Arrhenius equation. So then by the Arrhenius equation, a lower activation energy results in a faster rate. Okay. Because it's minus, it's e to the minus of EA. So lower activation energy, faster reaction. So you asked the question about could I ask something like the last test on the third page? Yes, my hope would be that because we've now had more experience with this, and because we did this actually both classes, that's the kind of answer I'd be looking for. And there would be sort of 5 or 6 pieces to that. But that's the logic. And we kind of skipped over that when we talked about SN1. There's one piece, though, that I didn't include, and that is, why am I concerned about the stabilities of the tertiary and the secondary carbocations? Why am I not concerned about the stabilities of the initial alkyl halide? Because,
For SN1, the leading group ability.
oh no, it does. Remember, leaving group ability always matters because the leaving group is in the rate determining step. So why is the tertiary and secondary carbocation important? Or why is their formation determined that the reaction went faster? Because is the rate determining step. To form the carbocation is the rate determining step. Now, the way I ask you the question of whether you form a tertiary or secondary faster eliminated that part of it. But if I said of these two reactions, which one goes faster and why, the complete answer would be the rate determining step is the formation of the carbocation. Tertiary is more stable. Hammond's postulate says it has a lower activation energy. Arrhenius equation says lower activation energy, faster reaction. Okay. So that's where I could go back and ask you that question again. I bit the bullet once in grading it, which wasn't actually that difficult because we had just been introduced to it. But I could go back and ask again to see that we've all kind of gotten to that same page. Because we use the Hammond's postulate all the time. Whenever we're forming a more stable intermediate or a more stable product, that the more stable it is, the lower the activation. We use that principle all the time. But this will probably be the last time that I explicitly outline it. From then on, I'll just go Hammond's postulate, blah, blah, blah. And that's the answer. Bobby?
What will you be giving with the exam? Like last time you gave us that one sheet and a periodic table.
I'll give you a periodic table this time. Again, I don't know what else you need. Probably not. There's going to be no naming. So I'll give you a periodic table, and then hopefully you have everything else. But you're going to have to do R's and S's. It'll be a combination of old exam 2 and old exam 1 with Newman's, chairs, R and S, SN1, SN2. Okay. All right, if you have any questions, come and see me. I'll be around extended hours, or send me an email. But otherwise, I'll see you on Friday.
Can I ask a question? So, this one we just